Is the screen visible? Right. Okay, so in the past few lectures, we had looked at the module on the interfaces in materials. We looked at what are the different kind of interfaces that can exist in a material between its various phases, be they single phase or multi-phase. And we looked at how the interfacial energies vary as a function of the kind of interface. Now here's the next module, which is on liquid to solid phase transformations. So now we have the foundation of basic thermodynamics, diffusion, and interfaces. Now we will start with the so-called real phase transformations. So the first one of it is called liquid to solid phase transformation. So we are loosely following the book by Porter Stilling. It has a few things which are good. It lacks in a few aspects. And in some aspects, it kind of provides way too much information for a undergraduate course. So I hope I can make up for that for the shortcomings and try to present it in a way that will be more appropriate for a UG course. So naturally, the first topic is now liquid to solid. We are directly dealing with that because, in a sense, liquid to solid phase transformations are, at least the nucleation part is a bit easier to analyze, which we will see in the upcoming slides. But before we start with the theory, I would just like to, first of all, give you a glimpse of where these kind of theories are actually used, what are the practical applications, and why are we learning it for in the first place. So that's what we'll now quickly browse through, and then we'll move to the actual analysis of nucleation, growth, and so on. So as you know, metal casting is a widely used technology for preparing all sorts of products. And some processes actually use metal casting that we melt a metal and then pour it into any form we want. And in many cases, we might actually melt the metal and pour it into the form that we actually want in the final end application. So here are some examples of that kind of scenario. So there are various foundry technologies. They can use various processes like sand casting, where we have a mold made of sand particles which are compacted together. Or we can have a metallic die. A die is a kind of structure inside which there is a cavity and into which we pour molten metal. That metal solidifies and we actually get the kind of part that we want. So that is another way of doing it. So here's what it typically looks like if you visit a foundry, and I hope you can get a chance to, we'll try to arrange some industrial visits for you during your 4-year BTech. So this is how a foundry looks like. We typically melt metals, and this is what is called as a ladle. So the ladle is being tilted and we are pouring the metal into, or the alloy, into some kind of molds, depending on the kind of applications of the part that the company is trying to make. So these are some typical examples of the components that we make by casting. Aluminum cylinder head is one, then there are other kind of housings and so on. So these kind of parts are often made by casting. And as you can imagine, that's why it's kind of essential to understand how solidification works. Because once we understand the fundamentals, then we can better control the process to get the kind of structure and properties in the final components that companies look for. So here's the latest kind of buzz, 3D printing. So in 3D printing, what we do is use a laser to melt powders. So here's actually a laser beam. We simply feed metal powders into that beam. Those powders melt, and by melting successive layers of such powders, we can construct 3-dimensional parts. That's why it is called 3D printing. So these are some parts, impeller and some other housings for the Ford Motor Company, which have been prepared by 3D printing. But the basic process used here is still metal solidification. And as it so happens, metal 3D printed parts actually have quite good mechanical properties in some cases. So that's where the analysis of how solidification occurs actually does help us quite a bit in gaining the most out of 3D printing when we want to manufacture parts for engineering applications. Now, this is just an example of how casting process can influence the microstructure. Supposing we have this so-called aluminum silicon alloys. It's a eutectic alloy, and we cast it into a metallic mold, and we also cast it into a sand mold. So it's often observed that there is a big difference in the kind of microstructure that we get in the material. So this is a kind of aluminum alloy cylinder head for automobiles, typically cars. Trucks still use, I think, cast iron cylinder heads, but this is used for cars. And if we use different processes, then it's observed that the microstructure is actually quite different. So in this figure A, you can see that the average grain size is about 100 microns if we look at the micron bar. So this could be typically what we get for sand casting. And if we go to metal die casting, such as figure B, the average grain size is only about 2 or 3 microns. So it's much finer than the grain size seen in figure A. And as you might recall from this Hall-Petch relationship, finer grain size typically leads to better mechanical properties, higher strength, hardness, as well as ductility. Now, grain size refinement is the only mechanism where you can get both high strength as well as ductility. So you can maximize both strength and toughness. Normally, these two parameters, these two properties don't go hand in hand. If you increase strength, typically it comes at a trade-off, and that trade-off is lower ductility. So that's why grain refinement is an interesting mechanism whereby we can actually get the best of both worlds. That's why there's a lot of interest in refining grain size by various technologies. And solidification happens to be one of those technologies where we can actually play around with the kind of grain size that we get in the material. Now, similar grain refinement is also seen for laser 3D printing. That typically we melt a part using melt powder using laser, and after it's melted, it also undergoes solidification relatively rapidly. So there's a rather high cooling rate for that solidification. And that high cooling rate, as it happens, leads to grain refinement. So that's why 3D printing is also of interest for getting high strength parts directly from metallic powders. So what's the fundamental basis? Why do we get such grain refinement? And that is the topic of our this module on understanding phase transformations. Now, of course, you might ask, not all parts are made by casting. Of course, what about things like car bodies or beverage cans? They are all made from cold rolled metal. We have sheet metal, and that sheet metal is undergoes various kinds of processes like stamping, punching, to directly get the kind of components. So typically these car bodies are made from sheet metal. There is a stamping die. So it's pretty much like a paper punching machine where we punch holes into a paper. So here we do it with sheet metal. The unwanted areas are removed by punching, and the areas which are actually go into making the car body undergo some kind of shape deformation to get the kind of final shape that is dictated by the application, which is in this case a car body. Likewise, we can have beverage cans. They all come from the same source. We have a cold rolled sheet metal, which undergoes various kinds of processes to get the final product. So you might ask, where does solidification come into picture in these kind of applications? Well, as it happens, these sheet metals, although we see this as a starting point, sheet metal, the sheet metal is in fact prepared initially from, it's a kind of intermediate product. The starting stage is anyway melting and casting. So as I will show you in the next slide. So what is known as ingot casting, hot rolling, cold rolling. So these are some of the processes which go into getting that sheet metal product. So there is some kind of melting, casting, and solidification involved, even if you are dealing with sheet metal product. It's just that you don't see it immediately, but it happens somewhere upstream in the processing kind of sequence. So these are typical steel billets. They are pretty tall, maybe like 10, 12 feet tall, about 6 feet wide maybe. So these are first cast into molds, and then these hot ingots actually undergo what is known as hot rolling. It's like a sugarcane rolling mill, kind of a crude analogy. So we put these hot billets into that rolling mill, and we get kind of plates or sheets by hot rolling. And here is another cold rolling mill, as we see here. So this hot rolled metal is undergoes cold rolling inside a set of rollers, as shown in this figure. It's a proper industrial workshop, and all of these. So as you can imagine, the starting point for all of these materials are essentially it begins with this as cast ingots as shown here. So although casting solidification may not be directly relevant, it does play a role in affecting the final structure and properties of the cold roll sheet. And there are certain things, for example, the grain size of the starting ingot, which needs to be tackled if we want to get optimum properties in the final product. So that's the long and short of the story. That's where solidification does play a key role in many engineering applications. So I hope this was a good snapshot of the kind of engineering applications that finally and actually utilize solidification technology at some stage or another. So what is the content of this module? So although I showed you some of the industrial photographs and so on, the actual industrial processing or the manufacturing processes won't be the focus of this particular subject. We'll have another DC subject later on industrial materials processing. So the focus of this subject will be on fundamentals. We will try to understand the mechanisms of nucleation, growth, and how the two combine together to give you what are known as time temperature transformation diagrams. And in this module, we'll look at their applications like solidification morphology, grain refinement, etc. And it's important to remember that although we are starting off with this module on liquid solid transformations, these three topics like nucleation, growth, and TTT diagrams are actually quite fundamental. So they don't apply only to solidification, but the basic concepts developed here will also apply to solid-solid phase transformations. It's just a matter of some prefactors and one or two terms being different, which we will discuss later. But the essential ideas that we'll be developing are pretty broadly applicable for any phase transformation which requires diffusion of atoms. So with this, we will now try to look into get started with this business of nucleation and growth. So is it okay so far? Yeah. What a good snapshot.
Yes, sir.
Okay, if you have any questions, let me know. So we'll now start with this business of solidification. So what is the driving force for freezing? Whenever we are dealing with, from your thermodynamics course, you might remember that whenever we are talking about two phases, say alpha and beta, that transform into each other, then as you know, there must be some kind of thermodynamic driving force. Only then certain phase will be more stable than the other phase. So if beta is more stable than alpha, say, then the free energy of beta must be lower than the free energy of alpha, right? So let us apply this concept to freezing or solidification. So here we have a free energy versus temperature curves for two kind of phases. The red curve is for solid and the green curve is for liquid. So as you know, here is the melting point, Tm. Above the melting point, as you can see, the liquid has a lower free energy and the solid has a higher free energy. So if we were at some kind of temperature, say T high, here the stable phase will be a liquid. At the melting point, both phases will be coexisting with each other. And as we go below the melting point Tm, let us imagine we are able to cool the liquid without solidification, without solid forming at all. Supposing by some means we are able to maintain the liquid below the melting point, and we reach some temperature T1. Then as you can see, now there is a free energy difference between solid and liquid. So the solid has a free energy somewhere here, and the liquid has a free energy somewhere here. So there's now a difference between the free energies of solid and liquid. And that difference, let us call it, it's a volume free energy. So let's call it delta GV at temperature 1, which is delta GV1. So as you can see, as we go below the melting point, there starts to develop a free energy difference between solid and liquid. And as we go further down, if we lower the temperature to T2, as you can see, there is the free energy difference, the delta GV2 is now greater than delta GV1. So this kind of tells us graphically that how a free energy difference develops between the parent and product phases. This is, by the way, a perfectly general argument. We can use this kind of figure for any two phases, not just solid liquid. But we are simply taking the example of solid liquid because it makes our further analysis just a little bit easier. So when I said we go to a temperature below the melting point, there is a particular terminology which comes into picture here. When we cool a liquid below its melting point, that process is called undercooling or supercooling. And the degree of undercooling or supercooling is defined as the temperature below the equilibrium melting point, Tm. So that delta T, which is the undercooling, is in fact Tm minus T. For example, here the undercooling will be Tm minus T1. At this point, the undercooling will be larger. Here delta T2 is Tm minus T2, and so on. So both these terms are used interchangeably. We can call it undercooling, or we can call it supercooling. So as we saw graphically, it's kind of based on the free energy curves. We can see that the driving force. So for any phase transformation, the driving force or the desire to undergo phase transformation is the free energy difference between parent and product phases. So as you can see, delta GV is proportional to the undercooling delta T. As we increase delta T, the free energy difference or the delta GV keeps on increasing. So that means there must be more and more incentive for the phase transformation to occur as the undercooling delta T increases. And by the same argument, if we go above the melting point, there is no driving force for solidification. But if you turn the argument around, you can argue that yes, there is a driving force for, if you are above the melting point, what will the driving force favor? The driving force will be for melting rather than solidification. So there will be driving force for the solid to transform to liquid above the melting point, and below the melting point, the driving force would go in the direction of solid. So this is something we saw intuitively in terms of figures and all. Now the question is, can we actually quantify this driving force delta GV? Yes, we can do it. So let us first derive the entropy of melting delta S Tm. So these are the standard terms, delta S is entropy of melting, entropy, delta S is entropy change, and delta H is the enthalpy change. So we'll define certain terms. When we say entropy of melting, that is entropy change at the melting point, we'll call it delta S Tm. Or we'll just simplify it to delta Sm, M for melting. Likewise, the enthalpy or the latent heat of melting, the enthalpy change on going from solid to liquid or liquid to solid at the melting point is given by delta HTM. We'll just simplify it to delta HM. So this is the basic terminology. And now we'll just do the usual thermodynamic equations. I'm pretty sure you might already know it, but just go through it. So let us define the free energy of liquid GL. It's defined as HL, where HL is the enthalpy of liquid minus TSL. SL is the entropy of liquid. Likewise, we can define the free energy for the solid GS, which is HS minus TS. So if there is a driving force delta GV, that driving force is the difference in free energy between solid and liquid. So it is GS minus GL, which can nicely be written as a term consisting of the enthalpy difference and the entropy difference. That can be further simplified as delta H minus delta S. So that means at any temperature T, we have this general relation delta GVT. It's not very surprising, but so if we are considering any temperature T, which is say below the melting point, then the free energy difference or the driving force delta GV at that temperature is simply related to the enthalpy difference between solid and liquid delta H and the entropy difference delta S between solid and liquid for that particular temperature. So that's the basic premise here. There's a basic concept. This can be fine-tuned further to actually get a more generally useful relation, which I will quickly show you. So let us try to get a nice relation for this entropy of melting. So you know that at the melting point, solid and liquid have the same free energy. So the delta GV at melting point must be 0. So that means delta HM minus TM into delta S at Tm must be 0. So simply put this equation, delta H at melting point equals melting point into entropy change at melting point. So here's a nice result that is a very useful result, which is what we get finally. The entropy change at the melting point delta S equals the enthalpy change at melting point delta H divided by the melting point itself. So I think this is known as Richard's rule or something. And this is what we had discussed in the interfaces class last week. So if this entropy of melting is very large, if it exceeds 4 times R, then we get sharp faceted interfaces. Otherwise, if the delta S, this entropy of melting is low, as it happens for most metals, then we get sharp, so then we get rough or diffuse interfaces. So the interface structure is, the transition from solid to liquid is very gradual. That was one of the physical significances of this particular relation. Now we'll try to apply it to get a more useful relation for the driving force. Let us now quantify this driving force delta GV further. So for low undercoolings, we can make a simple assumption as shown in the figures on the right. We will assume that even if we are below the melting point, say we are not exactly at the melting point Tm, we are slightly below that, then we are going to make a reasonable assumption that the enthalpy change on going from liquid to solid at some temperature T, which is slightly less than Tm, is still pretty much, it's not very different from the enthalpy of melting given by delta T. Likewise, we are going to make another assumption that the entropy change at some temperature T below melting point, a small difference, is not very different from the entropy of melting delta ST. This comes in very handy. So now we can actually write the free energy difference between liquid and solid for any temperature T as simply delta H for that temperature T, which is nothing. We have just made that assumption, so we are putting that delta H. So in fact, so here's the general relation above. So let us, this delta HT can now be replaced by delta H at melting point. This entropy at temperature T can be replaced by entropy change at melting point. Then we get the usual algebra and we arrive at a nice relation saying that the free energy difference delta GV, it's a volume free energy difference between liquid and solid at some temperature T below the melting point is equal to the enthalpy of melting delta H Tm into delta T divided by Tm. So as you can see, the free energy driving force is linearly proportional to the undercooling delta T. This result is of much significance. And this is what we had intuitively, graphically kind of looked at in the 2 slides previously where we saw the free energy curves for liquid and solid. So thus the driving force delta GV is proportional to the undercooling delta T. This result is very handy and will be used quite often in all the thermodynamic and kinetic analysis of phase transformations. Is it okay so far? Was this covered in any of your previous courses? Or is it new to you?
So this particular part is new, I think.
Is new. Okay, good. So I just wanted to make sure it's not too much repetition.
No, sir.
Okay, good. So here is a nice handy thing. So this was actually, I'll just draw, just to make the story complete. So here's what we had seen, and we had another equation. This was what free energy, and this was temperature. So this was melting point. This is solid. This is liquid. So as we see, as we start going below the melting point, from the graph itself, we can see that the driving force increases, and that is nicely confirmed, as it were, by the equation that we have on the right. So the free energy difference between parent and product phases, or the liquid and solid in this particular case, is linearly proportional to delta T, the undercooling. And the delta T was over here. This is temperature T, so this difference is, and this difference is delta GV. Okay?
Yes, sir.
Fine. Now the question is, suppose we are actually below the, say, we have a liquid and we are below the melting point. So does it mean that as soon as we come below the melting point, supposing here's a liquid, this is at a temperature T greater than Tm, and now we go to a temperature T2 less than Tm. So this is liquid. Thermodynamically, the solid is a stable phase. So what does it mean? How would the transformation actually occur? Does it mean that all atoms in this particular liquid will suddenly decide to come together and form the expected crystal structure, be it FCC, BCC, and would we get nicely like different crystals growing simultaneously, and the entire material is all of a sudden consumed and it suddenly magically transforms to a solid? Is that the case, or how does the phase transformation actually occur? So that is the key point. And as it happens that this particular scenario where we are saying that all atoms will suddenly decide to come together, the entire volume of the material magically instantly transforms into the solid phase is not a very likely scenario. Instead, what happens is certain groups of atoms come together and they form tiny kind of nuclei, and this is what we'll now be analyzing. So you still have the liquid and there are small particles of solid which kind of form independently, and these solid phases actually start growing, and eventually they start impinging, they collide with each other, and each of these crystals which are formed are what we call grains, and the boundary between those two crystals are what we were talking so far about, the grain boundaries. So the point is that these crystalline phases actually develop independently, independent of each other. They develop in certain spaces, certain regions of the liquid, quite randomly. So it's not like the liquid all of a sudden transforms to a solid, but it's a distinct two-stage process where crystals first nucleate and then they grow. That is how the entire volume of liquid is actually consumed. So here's an example. And like I said, phase changes, in fact, are usually not uniform throughout the material. And here's a day-to-day example of, say, boiling. Say we are boiling water. Once we reach the boiling point, it's common experience that we don't see that the water suddenly disappears. But we do get these bubbles, spherical bubbles. And any idea why the bubbles are spherical here? Why they're not square? Interfaces. System will try to minimize the interfacial energy between vapor and liquid. So the sphere would be the best shape which minimizes the interfacial area. And that is why these bubbles are always spherical. So the point here is this kind of simple analogy applies to many processes of nucleation and growth, where the second phase, in this case it was vapor, we can have solid from liquid, or if we are talking of two solid phases transforming into each other, alpha and beta, even then beta phase would first nucleate inside that alpha. It would form small regions, and then those regions would actually grow. So that is what nucleation and growth is roughly all about. But there is a caveat. It's not always true that all transformations do need nucleation and growth. Some transformations can actually happen all throughout the material suddenly, like spinodal decomposition. We'll maybe, if time permits, we'll briefly talk about that later in the course. But a vast majority of transformations do depend on nucleation and growth. So our focus now is thus on nucleation and growth. So let us first define. We kind of made a hand-waving argument and said, okay, particles form, this is nucleation, and then they grow, that is growth. There are slightly a bit more technical definitions. So like I said, here's a schematic. Here's a liquid, this big sphere, and supposing we have the green circles are solids. So what is nucleation? It is defined as the formation of the initial stable particle, which we call nucleus, of the transformation product. So let us say in this particular example, this particular solid A forms, that's a nucleus. So these nuclei can actually form independently throughout the whole volume of the liquid. I've just shown one here. You could also say that there can be another, another solid here, another nucleus forming over here, yet another over here. So it's a random process. It happens throughout the volume of the material. And once these nuclei form, what is the next step? That they will need to grow. But before that, let me just define the units of nucleation. So how do we define the rate? That is how fast these nuclei, these stable particles are forming. They are given by the number of such nucleating particles, these particles forming per unit volume, per unit time. So the units of nucleation rate are nuclei per meter cube per second. Okay. And then, like I said, these nuclei will grow. So we're given sufficient time. If we hold the material at a particular temperature, diffusion will occur. Atoms will keep coming from the liquid phase and they would like to join the solid, which has a lower free energy. And that leads to growth of these already nucleated particles. So look at this guy over here, this B particle. It's much bigger than the smaller particles labeled A. This was A. So this is because this B particle has actually grown with time. And if we have nice spherical particles, the growth rate is simply defined by G equals dr by dt, where r is the radius of that particle. So how fast does the radius grow with time? So this particularly applies for spherical particles. But just to be more precise, let us define the growth rate in more generic terms. Suppose we don't have a sphere, we have some kind of an irregular shape. Now, there is no clear radius. Suppose it's like a disk. Which dimension should be taken into account if we want to calculate the growth rate? Suppose this is A and this is C, and this disk is growing. How do we quantify the growth rate of this disk? That's a tricky part. So that's why a more general definition of growth rate is as follows. Growth rate is also defined as the increase in volume of that particle or precipitate per unit surface area of that particle. Is this clear? So supposing we have some irregular shape, its initial shape is this way, and then after some time it grows to a bigger, different shape. It grows in size. We can't nicely put some specific radius. So what we do is simply look at the increase in volume per unit surface area. So that's some kind of a idea of the linear dimension. So for a sphere, this ratio of volume to area is simply radius. So the more generic definition of growth rate is simply given by the increase in volume per unit area of the particle. So if you have a sphere and it nicely boils down to change in radius with time. And for most of our work in this course, we'll stick to the spherical assumption to make the algebra a bit easy. So we'll use dr by dt as the growth rate for a sphere. Any questions so far on this part?
No, sir.
And this growth rate is actually linear in this case. So it's meters per second. It's a change in radius with time. So, okay, let me discuss nucleation growth, and then let us see how this process actually occurs. So supposing we are looking at, we had that special ability to look at a high temperature liquid with our eyes or with some tool, what would we actually see? So these blue circles are atoms which are randomly arranged in the liquid. There is no crystal structure. So this is how a liquid would look like at a temperature above the melting point, or maybe even at some slight undercooling below the melting point. So actually what happens is, how do these nuclei form? So there's a fundamental process involved here. There's something called thermal fluctuations. So these atoms, as you can imagine, because of the thermal energy, they're continuously vibrating about their mean positions. And there's quite a bit of atomic mobility in the liquid phase. So it can happen that momentarily there's something that resembles a crystalline arrangement can form, such as shown by the green atoms. The atoms are not different. They're just being highlighted by that red circle. So all atoms inside this red circle seem to have something that resembles a simple cubic arrangement. Suppose this liquid is going to transform to a simple cubic crystal. Then it so happens that sometimes atoms can decide to come together just because of purely random thermal fluctuations. For a moment they are together, they form what are known as clusters. This is called a cluster or an embryo. Both terms are correct. They are not called a crystal yet, and I will explain that to you in a moment. But this is what a cluster or an embryo looks like. And these clusters or embryos are kind of ephemeral. They are transient. So they are here one moment, and the next moment they are gone because of the thermal energy. So once again, some such cluster might form somewhere here. It will exist for a few milliseconds maybe, and then it is gone. So this kind of process happens continuously. These clusters are formed, they are born, and they die. So this process goes on cyclically. So this cluster, that's why I written over here, clusters continuously form and then they dissolve back into the liquid. So that basically tells us that a structure of liquid is not a static fixed kind of structure. There are atoms which are wobbling around, they are vibrating, they have quite a bit of thermal energy. So by pure statistical chance, some such atoms can come together in a configuration that happens to resemble that of a crystal. Whether or not these clusters or embryos grow into a crystal is a different story. But this fundamental process, the formation of clusters or embryos, is an ongoing process. It always happens. It happens even in the liquid above the melting point, where there is no thermodynamic driving force for solidification. So although the liquid is purely completely stable, this kind of process of cluster formation and their destruction is an ongoing process. It always happens, And the reason is the thermal energy of these atoms. So they continuously vibrate around, and by chance, some of them can come together and give you something that looks like a crystalline arrangement, a crystalline cluster. It's a purely random event. It happens, they form, they go back, they again form somewhere else in the liquid, they again go back. But this is the fundamental process which is responsible for subsequent growth of crystals. That is what we mean by nucleation. We'll come to that in a second. So is this picture clear? This is quite important to understand. What is the physical basis for all of this nucleation and growth happening? Then we'll come to the thermodynamic arguments and the algebra. In physical terms, this is what is going on inside a liquid. Okay, clear? I hope so. So here's a nice kind of image taken from Cornell University. They have just done some computer modeling and tried to imagine what a cluster could possibly look like. Now we are going to assume spherical clusters, but as they are shown, in this case, it's a copper cluster forming in a melt of copper. As you can see, there are some kind of facets, there are faces developing here. We won't get into the too many details, but the basic argument is that although for all these textbooks and most of this analysis, we assume spherical clusters, in reality, cluster shape can be a bit different. And that is because once we have a solid crystalline-like cluster, different crystallographic planes will have a different interfacial energy with the liquid. So the assumption that the interfacial energy is constant is not actually true. Different planes can have different interfacial energies. So to minimize the interfacial energy, once again, a cluster can assume some kind of shapes which are not exactly spherical. But let's not get into that. It's a nice kind of visual, as it were, to show you how a spherical cluster or a sphere-like cluster would actually look like if we had the ability to look at atoms directly. So this is how these balls or many atoms have actually come together. Typically 100 or 50 atoms come together. They form this cluster momentarily. And because of thermal vibrations, the thermal energy, they once again disintegrate and they go back to the liquid phase from where they initially came from. And this process is ongoing. It forms, it's like a human birth. People are born and they die, and it's like a continuous circle. I don't know whether you have seen Shri Krishna's Vishwarup Avatar, and in that serial there used to be many people are coming and people are being born and many people are dying. So it's a continuous flux. So something like that happens here too. The clusters are born and then they die. So at some point, one of those clusters has to take the lead, and that leads to what is known as crystallization. We will look at that in a minute. So now let us look at the business of nucleation of a solid in a liquid. Now we talked about clusters. We are happy. We know that clusters, crystalline clusters do form inside a liquid. And whether or not that cluster actually goes on to get a promotion and become a stable crystal is a different story. Since these clusters are pretty small, they are forming and then they are dissolving again into the liquid. So at this time, we are not going to call it as a separate phase. We just call it a cluster or an embryo. So let us see what actually happens when such a cluster forms inside a liquid. Here we have a liquid, and inside that we have a spherical cluster as shown by this blue circle. So what's actually happening over here is that this area was once a liquid, and that is now replaced by a solid crystalline cluster. So what would you expect to happen? The volume which was once occupied by the liquid is now replaced by a crystalline cluster. So if we are below the melting point, then like we just saw, what would this mean? There should be a volume free energy reduction associated with the formation of this cluster, right? So the cluster formation would lead to some delta GV, which is the difference between the solid and the liquid free energies. And this term is negative because we are below the melting point. Supposing this was liquid, with plenty of atoms, and some part of the liquid has now decided to form crystalline clusters. So in this exact volume, there was previously only liquid that has now transformed into a crystalline cluster. So that means the free energy of this cluster will be lower than the original liquid from which it formed. And that difference between the two is given by this delta G. However, there is nothing free in this world, as they say. This reduction in free energy actually comes at a cost. And what is that cost? If we have this crystalline cluster, you can imagine there is now a distinct interface between the liquid and the cluster. So this is the interface. So essentially, we have a solid liquid interface. And as we saw in the previous module, such interfaces would mean broken bonds across the interface. So there will be a definite positive kind of contribution, free energy contribution because of that interface. So this is the point. There is also an added cost of the interface, and it has an interfacial energy called gamma. So what does it mean? So what is the net free energy change involved in the formation of such clusters? So if the net free energy change is called delta G, there will be two components. One is a negative component, reduction in free energy. It's minus delta GV into Vs, where Vs is the volume of this cluster. If it's a sphere, it's 4 pi by 3 r cube. And delta GV is the volume free energy reduction corresponding to the formation of this cluster from the liquid. But as we just saw, there is also an interface. So the interface will have a positive contribution. There's nothing free that will try to oppose the formation of this cluster. And hence this formation, this term is positive. Gamma solid liquid interfacial energy into the area of the interface. And where this delta GV, this free energy driving force or the reduction in free energy, is simply given by volume free energy of liquid minus volume free energy of solid. So there are two things happening when we get a crystalline cluster inside a liquid. One is the beneficial effect. Yes, crystal will have a lower energy. So there's a volume free energy reduction. But we also add an interface. So that is inevitable. Whenever something forms, there has to be an interface which forms. So that interface would now have a positive free energy. So there will be two terms in the net free energy change associated with the formation of this cluster. And those two terms are a volume free energy reduction, this one term. The second term will be the opposition term, which is the formation of this interfacial energy. So these are the two basic things which happen when a cluster forms inside a liquid. Whether or not this cluster is stable would really depend on what is the total free energy change, delta G, associated with the formation of this cluster. So if this delta G happens to be negative, then yes, the cluster is stable. But if that delta G, that free energy change is quite, it's positive, then that is bad. The cluster will not be stable. It will melt down and go back to the liquid. So here's the total free energy change. Written nicely for a spherical cluster. So here we have the usual equation. This is an important equation which we'll be often using. This is a volume free energy reduction, first term, and this is the second term, 4 pi r square. That is the interfacial area between a sphere and a liquid. So that is given by 4 pi r square gamma. Is this business clear to you, or any questions? Okay, I hope it's. So that means, like I just said in passing, not all nuclei or not all which clusters which form are states actually should be clusters. It's the wrong word. It should have been nuclei. Not all clusters are stable. The surface energy has to be compensated for by the volume free energy reduction. So we get an additional component, that gamma energy. So that has to be compensated by the reduction in free energy delta GV. Only then the total delta G will be negative. Otherwise, the cluster formation will not be beneficial for reduction of free energy of the system. So let me, okay. So here's just some further analysis of that same thing. Now we're just taking a closer look at those two terms. Supposing here we have the cluster radius r, and here's the total free energy change associated with the formation of cluster of radius r. So this is a cluster of radius r. This is solid and it forms inside a liquid. So there are two terms as we saw. This red curve shows the interfacial energy term, 4 pi r square gamma, and here's the volume free energy reduction term. So one term is positive, the other term is negative. Now, if you look at the ratio of surface area to volume, then that ratio goes as 1 over R, right? So surface area to volume for a sphere is proportional to 1 over R. So what does this tell us? If the radius R is very low, then surface area effects are bound to dominate. And volume effects, volume will be the dominating factor if the radius R is actually large. So this is what we can imagine in simple physical terms. So let us look at this free energy change delta G associated with the formation of a spherical cluster of radius R. We have two terms, free energy change minus 4 pi R cubed by 3 into delta GV plus 4 pi R square gamma. So what happens? Okay, I will just try to, well, we'll come to the derivative a little bit further. I will just explain this graph in the first place. This. So look at these two terms now. One term is actually increasing and the other term is decreasing. So if we try to add these two terms, this particular term will be dominant at low radius, this term will start becoming dominant at higher radius. So if we do a simple addition, actually you'll realize that there is a certain critical radius R star at which or beyond which the delta G will actually start becoming negative. So for any radius R below R star, that interfacial area is more dominant, and for some critical radius R star above which the volume term actually starts dominating, and that can be nicely derived in terms of a derivative. I will show you that in a minute. But if we simply add those two terms, then we just first will look at it graphically. As you can see, for R star, if there is some radius, if we increase the radius beyond R star, say we have a particle cluster which is of radius R star, and we keep adding atoms to that cluster so that the radius increases beyond R star. What would you expect? So at R star, the free energy is here, by the red dot, it will tend to decrease, right? As we travel along the delta G curve. So basically that means that all clusters with a radius more than R star can actually reduce their free energy further by consuming more and more atoms from the liquid. But if the reverse were true, if our free energy is over here, say our radius is somewhere here, which is R less than R star, then any addition of atoms to that particular cluster, so this is a smaller cluster. So if its radius increases, then as we can see that the delta G actually keeps increasing. So that is a bit of a problem. The cluster will not find it energetically favorable to increase in size. So how can it reduce its free energy? It will simply shed away all its atoms, give those atoms back to the liquid, and by doing that, it can actually travel further down this green curve and try to minimize its free energy. So that is why any cluster which has a radius less than R star, the delta G will tend to increase with the increasing radius, and the cluster will not be stable. If the cluster already has a radius of R star or greater, then actually it can reduce its free energy delta G further by acquiring more atoms from the liquid. So that means by increasing its radius further, it can actually lower its free energy. Just because of these two conflicting terms. One is a positive opposition term, the surface area interfacial energy, and the other is this volume free energy reduction term, which actually favors the formation of clusters. So one guy is favorable, the other term is unfavorable. So there has to be a balance somewhere in between. And beyond that tipping off point, that beyond that R star, things get more positive, kind of better for crystallization, and the clusters start to become more and more stable. Let's show you a bit more of that. Okay, let me just get all the kind of sentences I have. So what we are saying is that not all clusters or embryos are stable. Like I just talked to you, the surface energy has to be compensated for by the volume free energy reduction. So that's why we have a critical R star. And this volume free energy overcomes the surface energy only above a critical cluster radius R star. So that is what we just discussed. Below R star, surface area effects will dominate. Above R star, the volume term will dominate. That's why only above R star, your clusters will start becoming stable. And this term, this delta G star, this barrier of this critical, this change in free energy associated with the formation of a cluster of radius R star is called delta G star. So I'll repeat. A cluster which has that critical radius r star is called the critical sized cluster, and the free energy change delta G associated with the formation of this cluster size is called delta G star. So that is the work of nucleation, or the energy barrier or the activation free energy for the formation of a critical size cluster. So what it means in simple physical terms is the formation of a cluster must involve a free energy change of at least delta G star. Otherwise, the cluster is not stable. So we need to put in so much work that the free energy change delta G equals delta G star for R equals R star. And that height of that barrier, this particular barrier, is called the delta G star. That is the work of nucleation. So the higher is this barrier, more and more difficult will be the formation of these clusters. And the lower is the delta G star, the better it is for the formation of stable clusters. I will do the analysis. In fact, that will be very much central to the derivation of nucleation rates. But this is a physical picture that I wanted you to appreciate. Let me know if this is clear to you. Okay, is it clear or not clear? Fine. So I'll just first make a brief distinction. Note that we use the words clusters, embryos, and not crystals. So clusters and embryos are still part of the liquid. They are a temporary phase. They are continuously forming, and if the radius is below the critical radius r star, it's not energetically favorable for them to grow any further. So they die and they go back to the liquid. The clusters disintegrate. But if the radius of these clusters is more than that critical radius r star, then as we saw, they are happy to get more atoms because that would actually lower their free energy further. So all these clusters and embryos are basically, once they exceed the critical size, only then they are considered to be stable nuclei. So what we mean by stable nuclei is only once their size exceeds that r star, only when r is greater than r star, are those clusters stable, and then they form a distinct phase inside the liquid. And that phase can be considered a solid. So we say that a solid has nucleated when a cluster of radius r greater than r star has formed. So anything below r star is continuously forming and dissolving back. That is not stable. Once the size exceeds that critical radius r star, the system can actually lower its free energy further by getting more atoms. And that's why only those clusters which have a radius r bigger than r star can be considered a separate phase. And anything below a particular size given by r star is still considered part of the liquid, because they're not permanent, they're temporary. They're kind of forming momentarily and they are gone back again the next moment. So that's why, so this is the distinction between these two words, clusters, embryos, and crystalline nuclei. So this is the finer shade of meanings that needs to be grasped. Okay. So before we stop for today, I will just make this brief comment. So as you might have noticed, this idea of nucleation actually has similarities with business. So supposing we are starting a business, we need to put some investment. And if we don't make enough money, suppose the money we make is less than the investment we have made, then the business is naturally bound to die, right? It will dissolve. So this is what happens with clusters which have a radius less than r star. So they have put in some investment, and that investment is the interfacial energy, gamma. So that's a positive term. So there is nothing free. Like they say, there is no gain without pain. So if the crystals, the phase system wants to lower its free energy through the formation of clusters, the clusters would give you some reduction in energy given by the delta GV, but there is also an interfacial component. So that interfacial component is like an investment, gamma, and this delta GV minus delta GV free energy reduction is like the return on your investment. So only when this delta GV is greater than that gamma, so what it means is that only when the free energy reduction is greater than the contribution of that interfacial energy, only then those clusters will be stable. Similar things happen in real life. So if it's a business where we are investing much more than we are getting back, the business will shut down. And supposing we are actually getting more, earning more money than we have invested into the business, then our business will flourish. So that's a nice example. R less than R star, a dying business, and R greater than R star, that means flourishing business. So in the real world, it is money, and in this case of nucleation, it is free energies. One is the investment is the interfacial free energy, and the return or the benefit is the volume free energy reduction that goes with the formation of a crystalline cluster. So I think that, are there any questions on this so far, or we'll stop for today?
No question, sir.
Okay. Fine, then that's it. Let's stop for today. Thank you.
Thank you, sir.
Thank you. So Bharadwaj, you can close today's session.
Okay, Professor, thank you.
Thank you.